The PID controller, a useful node for minimizing the error in a system. For this tutorial, I will be using my PID trainer. The workshop ID is in the description if you want to download it. Let's say you wanted to line this blue cube up with this orange bar and keep it level with nothing but these thrusters. The PID controller would be perfect for this. Here's how you wire a PID controller. You take the value that you want to control, which in my case is the pitch of the cube, and you send that to evaluate and process variable. Then you send result to whatever you want to control that value with, which in my case is the thrusters. Now you can set the set point. This is the value that the PID controller will try to get the process variable to match. In my case it's 0 because I want the bar to be perfectly level. To tune the PID controller, first start with proportional. The PID controller will take the difference between the set point and the process variable, multiply that times the proportional value, and add that to the output. So if we set proportional to 1, it will take the difference between the pitch and 0, which is negative 26.3, and send that out, just like that. Now, just with proportional, we're on the right track, because when the bar is too low, it fires the bottom thruster, and when the bar is too high, it will fire the top thruster. But we're not quite giving it enough power, so we're going to increase the proportional. Now we're getting a little closer, so now increase it a little more, and now we're almost there. So you could just keep increasing it, but you eventually run into a problem where it oscillates a lot like that. This is where the derivative value comes in. The derivative value is sort of like a dampening effect. The PID controller looks at how fast the process variable is approaching the set point and multiplies that by the derivative value. So if we were to set this to 10, it should dampen it. As you can see, it's still overshooting it, so when it's all the way down, it shoots up past the line and back down, so that means you can increase it a little more. Now it's dampening too much, so you can go back down. You want it to shoot up right to the steady state as quick as possible and not overshoot it, just like that. Now we have a pretty good system. The cube moves straight to the steady state without overshooting it. But you may have noticed that it's not actually level, and that's because gravity is pulling it down. If we were to turn off gravity, it would work perfect. But with gravity, it's pulling it down. So we need some way to adjust to outside factors like gravity or more weight. Here's where the integral value comes in. Every time the PID controller is evaluated, it takes the difference between the set point and the process variable, multiplies that by the integral value, and adds that to the result. Because we're evaluating it 30 times a second, we want a very small integral value. Now the bar should adjust no matter what outside influences affect it. You have to be careful though, because if you're in a situation where it can't adjust enough, the integral will keep adding values. And this can lead to some problems. Say if your drone flipped over and it was just adding a bunch of integral like this, it'd be bad, because then you would walk over and you'd unflip it, and then it would freak out because the integral value is adding a ton. In this case, it's fine because we can just wait and it eventually will level out, but if you had a drone that was firing a thruster full power, it would be very bad. It would flip all out of control. If you ever need to reset the integral part of your PID controller, you can trigger reset. Now that you have a good working system, you can set the set point to whatever you want. This situation is just one use for a PID controller. In other situations, you may just need proportional and derivative, or just need proportional and integral. It all depends what you're trying to control.